Okay, so welcome to all of you and a very good evening. So today this is the extra or additional session for the Introduction to Fluid Mechanics course, and today it will primarily be a doubt clearing session. If anybody has doubt, they can join the session and ask their doubt, or else meanwhile, like what I will do is I will try to discuss a single topic that I felt that is kind of important for your understanding of the course. So I will just discuss this boundary layer theory because as I promised in the last problem solving session that I will discuss a boundary layer theory. So I will discuss our boundary layer theory briefly. I will just discuss the basics, very basics, and just give you a brief idea of the solution, and of course not solve the solution, but I'll just give you a brief idea of how to solve the boundary layer equations. I will give you an idea, and after that I will just briefly skim through all the topics that we have discussed from lecture 1 to lecture 12 so that a proper revision of the course is done. So I will just quickly go through all the basic concepts, just a revision for all of you who are watching the video. It will be a great source of revision you can watch, and meanwhile if there's any doubt by the students they can ask. We will try to clarify it. The discussions in the doubts asked and discussion from the forum has also been cleared, so it has been answered. And moreover, there were some questions regarding the previous year's question papers. So unfortunately we do not have, at least I do not have the previous year question papers with me, but I feel that going through the video lectures by Prof. Chakraborty would be more than enough for your exam. But still, since you need some self practice, I would suggest that you might want to go to a textbook of this particular course. The name of the textbook is Introduction to Fluid Mechanics and Fluid Machines by Professor S.K. Som, Professor Gautam Biswas, and Professor Suman Chakraborty. So you might want to go through that textbook for your reference. And the assignment problems for this course that has been done for this particular course from week 1 to week 12 would be more than enough for your exams, and the problem solving questions that we have done in the sessions would be enough, I guess. So with that, let us just start the boundary layer theory. So if you remember, in the last class we discussed about dimension analysis, and I told you that one of the important applications of dimension analysis comes in the boundary layer theory, where we need to understand the scales along which the velocity or the different flow parameters vary. Right, so it was one of the important applications, of course, other than the application in the experimental setup or experimental studies. So in the case of boundary layer, we will consider a very simple case. In a generalized case, the boundary layer can be over curved bodies as well. For example, flow over an aircraft, the surface of the shape of the aircraft is mostly curved surface. So in that case also boundary layer analysis is quite valid. So we can do that as well. But for the simplicity and the basic understanding of the boundary layer theory, I think we should consider with the very basic case, that is the flow over a flat plate. Okay, so in this case we consider a flat plate given by this black rectangle which has a width across depth of the paper. Okay, and we consider that the flow with an incoming velocity of u infinity strikes the leading edge. Okay, so these are standard terminologies, that the edge at which the incoming flow strikes is known as the leading edge, and the end at which the flow ends, like the surface over which the flow occurring ends, this edge known as the trailing edge. Okay, so and moreover you can here consider that the length goes on through this in this direction, but I've just drawn a part of it. So the flow strikes the leading edge of the plate at this point, and the moment the flow strikes the plate, there is a formation of boundary layer. Okay, so what boundary layer basically is, so it was discovered or formalized by Ludwig Prandtl, one of the very big names in the field of fluid mechanics and the founding father of boundary layer theory. So he devised that in the case of low viscosity fluids, the viscous effects are primarily what is located or situated in the in a region quite close to the surface of the object. Okay, so he formalized that, like for example, if there is an aircraft or if there is a vehicle, say I will just draw a simple diagram. Say if there is a car, okay, and it is moving in this direction, say, then say it is of course moving across air has a very low viscosity, then he suggested that in these kind of scenarios the viscous effects from the air is limited to a very thin layer attached to the surface of the car. Okay, so within this layer the viscous effects will be quite dominant. Okay, so it will basically mean that in this region the flow would have rotational effects and viscous effects would be highly present. Okay, but there will be very steep velocity gradients. Okay, and beyond this region, in this outer region, the flow then can be essentially be modeled as potential flow. Okay, so potential flow, again we have not discussed I think explicitly, but we have termed it again and again while discussing about the fluid dynamics and fluid kinematics part. So potential potential flow basically means that the viscous effects are negligible, or in viscid flows basically, potential or in viscid flows. So if you remember, when we discussed about this, when we first discussed about boundary layer in these problem solving sessions, I told that the formation of boundary layer and the fact that we are able to demarcate between the viscous region and the inviscid region, it does not mean that the flow viscosity is zero at the inviscid region. Okay, the flow viscosity is very much present because there cannot be any fluid which has a viscosity of zero. It's not possible. So the viscous effects are well present. Sorry, the viscosity is well present in the inviscid region, but the only thing is that at that region the velocity gradients are so small that they are not able to manifest the shear stresses from the surface of the object. Okay, so we know that shear stress is basically 2 mu Eij, where Eij is the uh, strain rate tensor, right? So basically this presents the strain rate tensor or the velocity gradients in a way. But since in this inviscid region these shear stresses are so small, the velocity gradients are so small, that's why these shear stresses also become almost equal to zero. Not because viscosity is zero, but the velocity gradients are almost zero. Okay, they are not zero, but they're almost zero. Okay, and that's what the basic definition of boundary layer is: the distance up to which the velocity is 99% of the free stream velocity, where the free stream velocity is denoted by u infinity. Okay, so let us go through it, then I think it will be much more clear. Okay, so this is how the boundary layer forms, and there is a clear demarcation between the viscous and the inviscid region, and this demarcation is formed by, as I already told you, so at this point, say we are considering the boundary layer at this point, the velocity at this point will be 99% of u infinity. I think I should mark it out so that it is clearer for the students. So at this point u is 0.99. I think I should draw it at the other end where there is space. Okay, so at this point u is 0.99 u infinity. Okay, why 0.99? This is primarily because of the fact that if we consider the point at which this velocity at this point at the boundary layer velocity profile becomes equal to u infinity, if we just consider it to be when we are trying to find the point at which u becomes equal to u infinity, then this boundary layer would have extended to almost a very long distance. So, and that makes the analytical study or the analytical approach to understand boundary layer very, very complicated and unintuitive, because intuitively told that we are interested in a very thin region close to the surface of the body, but it ideally it will take a very long time for the velocity to reach the free stream velocity. So in that case it thus becomes intuitively not clever to just find a point where u becomes equal to infinity. So that's why to make it analytically simple and intuitively understandable, what they did was they considered that the point at which your velocity becomes 99% of its free stream velocity would be your boundary layer. Okay, and this layer is something, it's not a, what to say, a visible carpet or a visible surface. It's actually an imaginary line, but this demarcation is very much present. Okay, even though this surface or this layer or this line is imaginary, but the effects and the concepts of boundary layer are very much present. Okay, the physical implication is not imaginary, but the physical structure, like what it means that there is no additional layer formation that you can see with your naked eyes or something like that. Okay, so I think it's understood, so let us proceed. Okay, yeah. Now let us consider one thing, that let us consider the point, and just to let you know, this boundary layer thickness at any point is indeed a function of x. Okay, it's not a constant value. So if you consider boundary layer thickness here or here, it will be different, and it primarily depends on the distance from the leading edge. Okay, so here x, this distance x basically means the distance from the leading edge. Okay, and say L is the length of the total plate. Actually it should be very long for proper understanding, but I have just drawn a very small part. Okay, but ideally this plate is comparatively longer, very long, compared to the boundary layer thickness. Okay, and as you can understand, this thickness, boundary layer thickness delta x, is a function of x. Okay, so it varies with the distance from the leading edge. Okay, and essentially it will monotonically increase in the, for the case of laminar boundary layer, the point up to which your boundary layer is laminar. But if in some way your boundary layer becomes turbulent, then again the analysis changes a bit. So we are just confined to the laminar boundary layers. Okay, and one more thing that you would have noticed is that your velocity profile. Okay, so again this is something like your velocity is 0 at the surface of the object, because of the fact that we have to impose the no-slip boundary condition. So because the no-slip boundary condition and no penetration boundary condition say your v velocity and the u velocity are both 0 at the surface of the plate, so it is 0. Now what happens is that your u, say the x velocity component, increases and then attains 99% of u infinity, and then in the in-viscid region, essentially, ideally this growth should slightly exist. I'm sorry for the drawing. So ideally it should be something like this. There has to be certain very slow increase in the velocity, and it then attains u infinity at some point far away from the surface of the object. But as I had mentioned, for analytical simplicity and better understanding and intuitive understanding, what we do is we consider that up to this point at the boundary layer, the velocity will increase, and then it will just stay uniform, implying the in-viscid region or the in-viscid zone. Okay, potential flow region. Similarly, as the flow grows, again the velocity will increase to a further distance because of the increased boundary layer, or the boundary layer thickness, and then again it will attain a constant velocity because of the potential flow region. Okay, so the interesting thing to know is that this velocity profile at this point and in this point are not identical. Okay, are not identical, they are different. So if you consider same layer at a point at the same layer in the boundary layer, within the boundary layer, say point A and B, velocity at point A and velocity at point B are different. Okay, essentially velocity at point A is actually larger than velocity at point B, primarily because of the fact that the viscous effects are essentially slowing down the flow more. Like as the flow develops in, like across the boundary or along the length of the plate, the momentum transfer from the plate to the fluid is felt more. Okay, so as we go deeper and deeper, say if the boundary would have grown something like this, then our velocity profile will be something like this. Okay, so it has to be a bit less in this region, so that as it grows, then it attains u infinity at a distance at a greater height compared to point velocity profiles at point A and B, and then again obtain the potential flow region. So velocity at this point would be again lesser than at point B. So basically, what I'm trying to, what it tries to imply, that the effect of the plate is felt more on the velocity profile as we go further deep in the boundary layer. Okay. So what the basic takeaway is, that these velocity profiles are not identical, not something similar to what we have seen in the case of, say, fully developed flow between two parallel plates, or the Hagen-Poiseuille flow, the flow between the circular pipe. We see that there is a very well known term, this fully developed flow. So fully developed flow implies that the velocity does not change along the axial direction, okay, or along the direction of the traverse. But in this case, you are seeing that u is indeed a function of x. So velocity profile will change as we go along the axial direction or along the x direction in this particular plate. But a very, again, another very important and crucial takeaway is that although these velocity profiles at these 2 points are not identical, but they are similar. Okay, I think I should write it. Velocity profiles in at 2 locations in the boundary layer, say BL, at 2 different axial locations are not identical, but they are similar. Okay, so this is a very important takeaway from our understanding of this boundary layer theory. So I would like you to just take this as take this as I said, because I'm not going to derive it explicitly, but the solutions that I'm going to show you about the boundary layer analysis, that unfortunately which I'm not going to derive, because I think it is beyond the scope of this basic fluid mechanics course, so I'm not going to solve it, but the solution that we get is obtained from this similarity analysis. Okay, so considering that the velocity profile, though they are not identical but they are similar, so considering this self-similar analysis, they obtain the solution, which solution is known as the Blasius solution. Okay, Blasius solution, self-similar analysis. Okay, I think the terminologies do not make an intuitive sense right now, but if you think about it a bit more, you will get an idea. Okay, and a very important, not important, but a very interesting thing to know is that this Blasius, or the scientist under who solved the or found the solution of the boundary layer, is indeed the student of Prandtl. I think I should write it. Ludwig Prandtl, who formalized the boundary layer theory. Okay, so the student of the founding father of the boundary layer was the one who indeed found the solution for the boundary layer theory. Okay, so a good story to know. the doctoral student of Blasius, or the one who found the solution of boundary layer, was indeed the father of boundary layer theory. Okay, I think that's again not a part of the course, but a good story to know. Okay, so yeah, so let us proceed further. I think by now you get an idea of what we are going to deal with. So I think I should just write it. So in this case, u is a function of x. Okay, yeah. So now let us see what are the assumptions that they make while solving or while trying to solve the boundary layer flows. Okay, so the first assumption is that we consider the flow to be steady, similar to what we have considered till now. Do we consider density to be constant? Of course, for simplicity analysis. We are also sometimes when we impose this rho equal to constant in the boundary analysis, we call these type of boundary layers as incompressible laminar boundary layers. Okay, and we consider a 2D flow. Okay, so basically the variation along the z direction is considered to be negligible, similar to the flow between two parallel plates. Okay, so now from this, since the flow is 2D, we again don't not consider the w velocity component and the gradients along the z direction. We do not consider that. So our continuity equation boils down to this form: dou v by dou x plus dou v by dou a is equal to 0. Okay. Now from here, we define our Reynolds number by considering the length of the plate as our characteristic length scale. Okay, and u infinity, there is a free stream velocity as the characteristic velocity. So with that, the Reynolds number can be REL. When REL would mean that we are defining this Reynolds number based on the length of the plate. Okay, so if you remember, in the case of this flow between a flow in a pipe, I define Reynolds number as something like RED. So these are not random notations. Okay, the subscripts do have a very crucial meaning, and RED basically meant that we are defining the Reynolds number based on the diameter of the pipe. Okay, since there are no scope of diameter in this flow over a flat plate, and the characteristic length scale is indeed your length of the plate, so we say Reynolds number to be REL, that is Reynolds number defined in terms of the length of the plate. You can also define Reynolds number something like REX, where your Reynolds number will then be something like u infinity x by mu, and this Reynolds number is also sometimes known as the local Reynolds number. Okay, or local Reynolds number, because this Reynolds number is defined at a particular point where you want to find the Reynolds number. Because see, let me go back. So as I told you, x is the distance from the leading edge. Okay, so Reynolds number at this point and at this point and at this point, even though the flow is steady and density is constant, will change. Okay, and from this you get an idea that since the Reynolds number is not constant, and indeed varies continuously along the length of the plate, you get a brief idea that this type of flow over a flat plate is not a fully developed flow and is indeed a continuously developing flow. Okay, so as we go along the depth of the plate, your Reynolds number will continuously go on increasing. Okay, and your boundary layer thickness will also go on increasing, because these are continuously developing flows. Okay, there is no scope of these kind of flows becoming fully developed. Okay, so this is a very important again point to take away, that these kind of flows are not fully developed flows, but they are continuously developing flows. Okay, and okay, so we consider that if the Reynolds number is less than 10 to the power 5, if say at any point if your Reynolds number is less than 10 to the power 5, your flow is laminar for this flow over a flat plate. Okay, and if it is say greater than 5 into 10 to the power 5 into 10 to the power 5, then we consider that, or just say if it is around 10 to the power 6, we consider that the flow to be turbulent. Okay, so Now what we'll do is we'll look into the continuity equation and let us see how we can understand the scales of the problem. Okay. So if you remember, while discussing the flow over a flat plate, flow between two infinitely large plates or flow in a circular pipe, I told that those were exact solutions because we are solving the exact Navier-Stokes equation. Of course, after simplifying the Navier-Stokes equation to some ODEs by considering some important assumptions. Okay. But those are exact solutions. There were no approximations used while deriving the solution. But this boundary layer solution is indeed an approximate solution because we consider the cases where we consider, say, some limits. Say, for example, we consider that, say, the Reynolds number is very, very large. So these approximations, say, of this Reynolds number being very, very large implies that these are indeed solutions for a given limit or for a given range of Reynolds number rather than the entire velocity field, rather than the entire flow field, right? So this gives us a solution valid within a given range or within a given assumption where your scales vary accordingly. Okay, so I think this idea you will get much better sense when we proceed further. So the why I introduced this argument is that we need to do some scaling analysis to solve these boundary layer equations. That's how the solutions of boundary layer equations were obtained. Okay, by considering some basic scaling analysis. Okay, so what they do is since they found out that it's not possible to find analytical solutions for the entire equation, Navier-Stokes equation in the boundary layer, let us see which terms are dominant in the viscous region, because we know that there is a clear demarcation between the viscous and the inviscid region, and of course there is a scale difference that this viscous region is limited to a very small region, that is the boundary layer thickness, that is delta. So let us see whether this scaling of the region has some impact on the solution of the boundary layer theory. And after they found out that indeed they had the clear-cut implication which eventually helped them to find a solution. Okay, so they told you, okay, let us try to find the important scales or the scales that govern this velocity field and the length scales. Okay, so within the boundary layer, okay, so this solution is for the region within the boundary layer. Okay, let me consider that your velocity u along the x direction will vary as u infinity. Okay, so one way or another your velocity along the axial direction varies as the free stream velocity. Okay, so I will say our free stream velocity along the x direction varies as u infinity, so it will scale as u infinity. I'm sorry. Then the distance along the direction of the plate will vary as the length of the plate, right? And I do not know about how your velocity along the y direction will vary, so let it be, say, v infinity, and your distance along the boundary layer thickness will vary as the boundary layer thickness, right, delta, right? So because if you remember, if you see that the y direction is along the boundary layer thickness, right, that's why our y coordinate will vary as the boundary layer thickness. So that's what our assumption is. And now if this equation is valid, like homogeneous, if this equation is valid, then we impose the condition of homogeneity, that all the terms in the equation should also scale similarly. The scales of both the terms should be same, right? Since both of these terms are important, and it's a very important consideration that we cannot neglect any term in the continuity equation, because it's the concept of mass conservation. So both of these terms has to be equally present or equally scaled in the mass conservation equation. That's why the scaling of both these terms should be similar, okay, or almost the same. So that's why we say that u infinity by L should be similar to v infinity by del or delta. Okay, so from that we get an idea that v infinity, I think I wrote it incorrectly, so v infinity or the scaling of the velocity along the y direction would vary as u infinity delta by L. Okay. And if we impose this condition, and I think by now you already know that the thickness of the boundary layer is much lesser than the length of the plate, so your delta by L is much lesser than 1. Okay, so it would basically imply that if this is the case, then your velocity variation along the y direction should be much lesser than the velocity variation along the x direction. Okay, so that's why basically gives us an idea that your v infinity scales much lower, or has a scale much smaller than the variation of the velocity along the x direction, that is u infinity. Okay, so basically v infinity is much lesser than u infinity. So that's one of the conclusions that we get from the scaling analysis of the continuity equation or mass conservation. Okay. So I'll wait for a few minutes in this slide. So say I will wait for 1 or 2 minutes. So this is the conclusion that we get from your mass conservation or the continuity equation, that the velocity along the y direction varies as u infinity del by L, and since delta by L is much lesser than 1, so v infinity varies, basically v infinity is much lesser than u infinity. Okay, so this is the conclusion that we get. So now let us look into the y momentum equation, and let us see if we do the similar scaling analysis, what conclusions do we obtain. Okay, and this is very important actually. This is the most important equation in the boundary layer theory. So let us see how it varies. So we consider the flow to be steady, so the unsteady part is equal to 0, and the y momentum equation in the case of flow over flat plate will be u dou v by dou x plus v dou v by dou y would be equal to minus 1 by rho dou p by dou y plus nu dou square v by dou x square plus dou square v by dou y square. Okay, and now again we have to do the scaling analysis, and let us see how the individual terms in this equation vary. Okay, let's go term by term. So u will vary as u infinity, that we already found out from the continuity equation, and v will vary as v infinity, and x varies as L, so this term varies as u infinity v infinity divided by L. Okay, similarly this term v dou v by dou y varies as v infinity square divided by delta y, where delta y or y varies as delta, so we have, sorry, dou y varies as delta, so it will be delta. The interesting thing is pressure. We do not know how pressure varies as, but since we know that in the case of boundary layers, it is the inertia of the flow that drives the flow, or that causes the flow to occur, so your pressure will vary as the inertia term, that is indeed the kinetic energy of the flow. Correct. So your delta p will scale as rho u infinity square. Okay, and if it would have been the case where, say, the viscous effects or the viscous forces would have dominated the flow and inertia term would have been negligible, then your pressure would have scaled as the viscous terms. Okay, so it is again a bit, it takes a bit of intuition to understand it properly. So I think again I'm going beyond the scope of this course, but just wanted to imply that this scaling of pressure as rho times u infinity square is not universal. Okay, so if at all some scenario arises where your viscous effects dominated over the inertial effects, then your pressure would have been scaled as the viscous terms, not as the inertia terms. Okay, so considering that we know that the flow is driven by the inertial effects, so we will consider in this case, at least for the boundary layer, your delta p will vary as rho u infinity square, as the kinetic energy term. Okay, I think I should just write it for your reference. It is not universal. Again, this will not be asked in your exam or of this course, but something important for you to know if you want to proceed for, you want to take a career in fluid mechanics or study fluid mechanics further. Okay, yeah, so let us impose that and see what happens. So 1 by rho will be there, then pressure varies as rho u infinity square, so we have rho u infinity square, and delta y varies as dou y varies as delta, correct. Now let us see the viscous terms. So we have nu dou square v by dou x square, so nu will be there, the kinematic viscosity. This v varies as v infinity, and your delta x dou x square will vary as L square, correct. And we have nu dou square v by dou y square, so we have nu v is v infinity and y varies as delta, so we have delta square, okay. So I don't want to again go why we're considering delta square and why not v square. So it's a very simple logic, so I don't want to go to that, okay. I think that you should already know. So now let us see which other terms that we can clearly cancel out in this case, okay. So you can see I have cancelled out one term altogether. Why? Because we already know that v infinity scales as u infinity times delta by L, okay. So contribution of this term, that is v infinity square by L, clearly seems that would be very less compared to all the other terms, okay. I'm not saying all the others, but at least from the perspective of this from this equation, you will see that since v infinity square itself is very lesser than u infinity, and we are considering v infinity square and again dividing it by a very large quantity L, which is larger than L is very large than delta. So you can understand that the contribution of this term in this whole y momentum equation will be very less. So you can directly cancel out the contribution of this term from this equation, okay. That's why I directly consider it to vary as 0, okay. So it will be very less compared to all other terms, okay, because it's again intuitively understood, right? If you just again simplify it even further, so both of these terms, if you just substitute the value of v infinity as u infinity delta by L, again this is obtained from the continuity equation. So if you do that, if you substitute it here, you will see that v dou v by dou a varies as u infinity square delta by L square, okay. So even if you compare this term and this term, you will see that this term will be very less than this term, so we can easily cancel out the contribution of this term from the y momentum equation, okay. I hope this approximation and this cancellation of the terms are understood. I won't say it's 100% clear at the first go. It's difficult to take it in the first go itself, but at least why we are cancelling this term, it is understood. Just take this scaling, okay, then you will understand why it can be easily cancelled out, okay. Okay, so this term is very small, so it is 0. So now we have the other terms. There is a viscous term from this term, then the pressure gradient term, and the advective terms, right, the acceleration terms or the inertia terms. So now let us see how they vary with each other, okay. So what we'll do is we'll take the ratio of the inertia term and the pressure gradient term, okay. So we have u infinity square delta by L square divided by u infinity square by delta. So now if you simplify it, so this will get cancelled out and this will go in the numerator, so you will have this ratio to vary as delta by L square, okay. And since we know that delta by L is much lesser than 1, so delta by L square will again be very less than 1, so you will see that the inertia term turns out to be very small than the pressure gradient terms, okay. So again, the contribution of both these inertial terms in the y momentum equation can be cancelled out compared to the pressure gradient term, okay. So now the only term left to understand or see how it scales is the your second order derivative with respect to y, that is the viscous terms along the y gradient, okay. So let us see how it scales. Again, we'll take the ratio of viscous term by pressure term. So we have nu u infinity delta L divided by u infinity square by delta. So if we rearrange it, cancel out some terms and rearrange it, you will find that this scales as nu divided by u infinity by L, which is exactly 1 by the Reynolds number, okay. And one implication or one assumption that we take is that this Reynolds number are very large in the case of boundary layers, okay. So if we do that, then only your boundary layer thickness becomes very small, and these two assumptions are coupled in a way. So if this is considered, this is implied, and if this is considered, this is implied. Okay, these are coupled with each other in a way. We will see again how it is there, but this is the case. So these two assumptions we have to explicitly take, that your boundary layer thickness is much lower than the length of the plate, and Reynolds number is very larger than 1. So if this is the case again, then the viscous terms is again very small compared to your pressure term. So you can see that comparing all the terms in the Y momentum equation, the only term that has a considerable magnitude, or which is a highest magnitude in the Y momentum equation, is the pressure gradient term. So from this, the conclusion that we get is that your dou P by dou Y is almost equal to 0. Okay, and since there is no other terms to equate it with, so it will mean that dou P by dou Y is equal to 0. Okay, so this is a very important conclusion from the perspective of the boundary layer equations. So it basically tells us that, if I go back now, go down, so you will see that the thing. So if from the Y momentum equation we get that dou P by dou Y is equal to 0, so it implies that pressure is not a function of Y coordinate in the boundary layer. Okay, so within the boundary layer, pressure does not vary along the depth of the boundary layer. Okay, so it is a very important conclusion, and we will see why this, how this conclusion helps us to simplify our equations even more. Okay, so I will wait here in this, zoom out I think a bit. So I will wait in this slide for say 1 or 2 minutes. So if there's any confusion in this slide, please let me know on the scaling and all the other ratio. If there's any doubt, you can let me know, and then we will resume our discussion with the x momentum equation. So just to let you know that this session is an extra session, so which I am taking. So in boundary layer theories, this, or at least this discussion that I do, that I am doing, will not be asked in your exam. Okay, so because boundary layer theory is not a part of this basic fluid mechanics course, but since we have taken some examples of boundary layers in our momentum equation, in the equations, while discussing RTT, and even in the control volume analysis, so I thought that, and moreover, boundary layer theory is an integral part of any basic fluid mechanics course. So I thought that just for the sake of the students and viewers watching this videos, I think boundary layer discussion would be very helpful, at least knowing that this kind of theory exists, and to understand why the scaling analysis, the dimension analysis is very important for these kind of problems. Okay, so nevertheless, let us proceed further if there is no question. So, but just to clarify again, this boundary layer discussion won't be asked in the exam. It will now, eventually it will say, our discussion will end in say next 5 minutes or 10 minutes, and after that I will just go through a basic revision of the entire course, just skim through our topics. So if there's any doubt, you might ask, otherwise that would be all. Okay, but since this is an extra session, I thought I can take this topic for the help of just to help out the students. Okay, so this is the conclusion that we get, that the pressure gradient does not vary along the y direction within the boundary layer. Okay, so it's only varied within the boundary layer. So now let us take the x momentum equation and let us see if we are able to do similar cancellations or similar simplifications in the x momentum equation. So the x momentum equation tells us u dou u by dou x plus v dou u by dou y is equal to minus 1 by rho dou p by dou x plus nu dou square u by dou x square plus dou square u by dou y square. Okay, again unsaved term is cancelled out because we are not considering the flow to be steady. Okay, so now let us again see how these terms individually scale as. So u dou u by dou x will scale as u infinity times u infinity divided by L, so it will scale as u infinity squared by L. Okay, the next term is v infinity times u infinity divided by L, Okay, and since V infinity scales as U infinity delta by L, if you just substitute that in this scaling, you will eventually end up for it to scale as U infinity square by L. Okay. Now let us see the pressure gradient term. So we will have 1 by rho U infinity square by L. So again it is scaling as U infinity square by L. Very good. So all these terms you can see now have the same scaling. So at least considering these two terms and this term, we cannot cancel out any of them. Now let us see what the viscous terms gives us. Okay. So we have nu U infinity by L square. The first term will scale as U infinity by L square. The second term will scale as nu U infinity by delta square. Okay. Now the key thing here is that what term can be cancelled out? Okay. So if you look these three terms, this and this, these scale as the same. Okay, there is no difference in the scaling. They identically scale as U infinity square by L. Okay. I think using identical is a wrong term, so I will say they scale similar to U infinity square by L. Okay, but look at these two terms. Okay, so these two terms are the crucial part. So if you compare these two terms, only these two terms, okay, so you will see that this term, the pressure as the gradient, the velocity gradient along the y direction has a much higher magnitude compared to this term. Why? Because since delta by L is much lesser than 1, and even if you take the ratio of these two terms, you will find out that the order of magnitude of this term is indeed much higher than this term. Okay, and thus from this equation, the only term that we can essentially cancel out, let us just take the ratio. I think that would be better. So I will say dou square u by dou y term. Now I think I should take the other way around. Dou square u by dou x square, dou square u by dou y square. I think it's wrong, so I will write something like order of dou square u by dou x square and divided by order of dou square u by dou y square. Okay, so if you do it, you will have nu u infinity by L square. This is nu u infinity by del square. If you do it, you will have scaling as delta by L square. Okay, so it implies that your y gradient along the y direction, velocity gradient along the y direction, is much higher than the velocity gradient along the x direction. So this term can be effectively cancelled out from this equation. Okay, but the similar cannot be said for all other terms. Okay, because even though this term scales as U infinity square by L and this term scales as U infinity L square, but you will see that since this term scales as U infinity square and this term scales as U infinity, so at least in terms of numerator, this term scales much higher than this term. Okay. Moreover, this term also has a product with the viscosity nu, which is usually much less, very small in the case of high Reynolds number flows. Okay. That's why if you do the scaling in a way and also intuitively try to understand, you cannot effectively cancel out these terms. Okay. That's why all these terms, the inertia terms, the pressure gradient term, and the velocity gradient along the y direction will exist in the case of the x momentum equation, and only the velocity gradient along the x direction can be cancelled out. Okay, and it can also be intuitively understood because, say, if you're considering the momentum analysis for a boundary layer along the x direction, okay, say the x momentum equation, then you can understand that the velocity variation along the x direction would be much smaller compared to velocity variation along the y direction, right? Because boundary thickness itself is very small, and any interesting physics that will occur within that small region in the boundary layer. That's why the velocity gradient along the y direction, which intuitively becomes much larger than the velocity gradient along the x direction. So this term essentially cancels out, and we cannot cancel out these other terms, because if we cancel out them, then there is no term that tells us the source of the flow. Okay, so these terms imply inertia, which are indeed the source of the flow. These are terms that generates the flow. So if we cancel out these terms altogether, then there is no flow, right? Then there is no point of solving the equations. That's why in that sense also we cannot cancel out this equation. And also mathematically also, if you do the order of magnitude analysis, there is no clear-cut way in which you can cancel out these terms. Okay, you will not get ratios of del by L or REL to cancel out accordingly. Okay, so the final boundary and finally one more assumption I forgot to apply, that is this conclusion that we get from the y momentum equation. So if you remember, we got a conclusion that dou p by dou y equal to 0, and p is a function of x and y originally, but since p is not a function of y as a conclusion from the y momentum equation, then p becomes only a function of x. So we can essentially convert this pressure gradient along the s direction from an PDE to an ODE, so it will become dp by dx. Okay, moreover, since, let me just draw the boundary layer it's a very rough sketch, so that, yeah, so as I told you, this is the velocity gradient. So pressure here outside the boundary layer will be P infinity, that is the pressure at the inviscid region. Okay, and pressure inside the boundary layer will again vary as P, which is a function of x and y. But from here we got, from the y momentum equation, we get that P is only a function of x, so P is a function of x only. And since we know that pressure at a particular location is independent of the depth of the boundary layer, okay, so it does not vary along the depth of the boundary layer, so pressure at this point will be same as pressure at this point, correct? Because pressure does not vary as the y coordinate. So if that's the case, for a particular location, we can simply write, and of course P infinity is ideally is also a function of x. So if that's the case, and since pressure does not vary as y, so we can just replace P as P infinity, because P does not vary as y, so we can write dp by dx as P infinity by dx. Okay, and we consider all of these and find the final form of the boundary equation. So we end up with this form, that is, the equation that we need to solve is dou v by dou x plus dou v by dou y equal to 0. There is no cancellation in this continuity equation, and the x momentum equation boils down to this form, that is u dou v by dou x plus v dou v by dou y is equal to minus 1 by rho dou p infinity by dx, sorry, minus 1 by rho d p infinity by dx plus nu dou square v by dou y square. And this equation I kept as star because this is not an equation that we need to solve, but the implication of this equation is this term that gets simplified. And the assumptions used are that the boundary thickness delta by L is much lesser than 1, and the Reynolds number is much greater than 1. Okay, so this is the general boundary equation that we consider for any kind of surfaces. Okay, this is a general boundary equation. But if you remember, initially we considered that in our case we considered the flow over a flat plate. Okay, so we'll try to see whether considering the flow over a flat plate helps us to simplify the equation even further. Let us see if it has any implication or not. Okay, so for a flow over a flat plate, we have the outer free stream velocity as u infinity I cap, that is velocity along the x direction, and for constant density we can essentially apply the Bernoulli's equation in the inviscid region. So we will have P infinity plus half rho infinity square is equal to C. Okay, now if we take the derivative of this equation with respect to x, we have dp infinity by dx plus rho u infinity times du infinity by dx to be equal to 0. Okay, now since u infinity is constant in the inviscid region, right, it's not a function of x or anything, it's just a constant value, so then du infinity by dx is equal to 0, which essentially tells us that dp infinity by dx is also equal to 0. Basically pressure is constant. right? The pressure at the free steam has a constant value and does not vary along the x direction. That's why, if that's the case, I will not say P infinity is constant. I will say that P infinity does not vary with the it does not vary along the x direction. So if that's the case, then this term dp infinity by dx is also equal to 0 in the case of flow or a flat plate. Okay. So if that's the scenario, then our x momentum equation simplifies to only this equation. Okay. U dou u by dou x plus v dou u by dou y plus nu dou square u by dou y square. I should write it explicitly for flow or a flat plate. Okay. So you can see that the equation that we need to solve for flow or a flat plate and in the boundary layer simplifies to a very simple equation, that is this equation and your mass conservation equation, that is the continuity equation. So you can see that there are two equations and two unknowns. There is u and v. Pressure we are not considering here, so we have only two unknowns, u and v, to find out. Okay. So at this form, it might seem that it is like, of course it has been simplified a lot, but still it's very difficult to solve this equation in its raw form. Okay. That's where the self-similarity analysis comes into picture. So that's where Blasius comes into picture. So Blasius is now evident. So Blasius and the self-similarity solution. So self-similarity solution basically means that he assumes or considers that even though the velocity profile is not identical along the axial locations in the boundary layer, but they turn out to be similar. Okay. And imposing those assumptions or those conditions, he was able to obtain the solution of these equations. Okay. So I'm not going to solve it. I'm not going to solve a solution, unfortunately, but let us see what solution does he get from from his analysis. Okay, which was again a pioneering work by Blasius. Okay, and again, which acted as a very fundamental base or a fundamental pillar of the subject of fluid mechanics. So now let us see if we scale these terms for a flow or flat plate, what conclusion do we get? Okay, let us see what we get. So both of these terms, if you remember, in the x momentum equation, scales as u infinity squared by L, and we have the pressure, the gradient along the y direction, the velocity gradient along the y direction, or the viscous terms with only velocity gradient along the y direction, to scale as nu times u infinity by del square. Okay, nu is there, it will be scale as u infinity, y square will scale as delta square. So these two terms are similar. So if you do it, you will have, if you just simplify it even further, you will get delta square by L to scale as nu by u infinity. Now if you just multiply L in both the denominators, you will get delta by L square to scale as nu by u infinity times L, or 1 by REL. Okay, or you will eventually get delta by L to scale as 1 by square root of Reynolds number. Okay, so as I told you, these two conditions are not independent conditions, but rather two coupled conditions. So if you take the condition that your delta by L is much lesser than 1, then you will eventually end up with the fact that the Reynolds number has to be much greater than 1. Or if you other way around, if you consider the Reynolds number to be much greater than 1, then your delta by L will again eventually end up with the ratio being much lesser than 1. Okay, so these are coupled conditions. Although even earlier it seemed like these are two separate conditions, but no, these two are actually coupled conditions that we have to apply while solving the boundary layer equations. Yeah. So as I was saying, the Blasius solved the boundary layer equation. Blasius is the name of the scientist who solved these boundary layer equations by imposing a self-similarity condition. And what he found out, that his solutions, although approximate but brilliant solutions, tell us that delta by x for laminar boundary layers, delta by x, which is delta is the boundary layer thickness and x is the distance from the leading edge of the boundary layer, scales as 5 by the square root of the local Reynolds number, where Rex is u infinity x by L, where x, I should write, is distance from the leading edge. distance from the leading edge of the flat plate. And CFX is the friction factor, okay, the fanning friction factor, scales as 0.664 divided by the square root of your local Reynolds number. Okay, so these two are actually very important solutions in the case of floor flat plate for boundary layer. Okay, and which turned out to be, I would say, very brilliant on the part of Blasius, where he was able to obtain the solutions, or at least give us an idea of how the boundary layer thickness varies in the case of floor flat plate. Okay, again, these are valid for floor flat plate. Okay, so yeah, if you want, I think again this solution, the detailed solution is again very fortunately given in the textbook by Professor Chakraborty, the textbook, the course textbook. There is an introduction to fluid mechanics and fluid machines by Professor S.K. Soam, Professor Gautam Viswas, and Professor Suman Chakraborty. So that textbook has this solution. So if anybody is interested, can of course go through it and see how brilliantly Blasius found a solution for floor flat plate. Okay, and if I'm not wrong, this turned out to be the last uh, evident progress in solving the Navier-Stokes. Okay, like beyond that, I do not think anybody could have made the considerable progress in solving Navier-Stokes equation, or at least the analytical solution of Navier-Stokes equation. So that's why these solutions are so brilliant. But even then also, these are not for a fully 3D flow and are not exact analytical solution. These are approximate solution. That's why, of course, this does not reduce its credibility, but just saying how much difficult it is to find analytical solutions. Okay, so that's all from my side in the boundary layer theory discussion. So if there's any doubt, so I'll wait for 2 minutes, say till 7-8. I'll wait for 2 minutes. If there's any doubt, you might ask regarding the boundary layer theory at least. And if not, then I will just, for the next half an hour, I guess, I'll just quickly go through the entire course, just skim past it very fast as a revision. And if there's any doubt in any particular portion, you might ask. I will try to resolve it today itself because this is the last session. If not, if for some reason I'm not able to clarify like properly, you can put that doubt in the discussion forum. I will actively be present in the discussion forum in the next few days till the exam, so I will clarify the doubts there. Okay, I'll wait for 1 more minute and then we can resume the discussions. Okay, then if there's any no doubt, so if there's no doubt at all in the boundary theory, and if you do not want, so I will not discuss anything new today. So if no doubt, students might like leave the session as well. But if there's any specific doubt regarding the course, they might ask. I'll just quickly go through the entire course once. I think that's the least we can do. Sorry. It will basically be a reading from mine. I'll just go through the concepts. I might tell you what are important. So let's just go through it briefly, okay? So from in the first week, we basically, it was the foundation of our discussion. So we introduced the concept of microscopic and macroscopic approach, so which eventually turned out to be the demarcation between Lagrangian and Eulerian approach. Right, so macroscopic implied to the Lagrangian approach, where we treat each and every particle for analysis and see how the velocity change, how the particles, and particles in this case, from this our course perspective, would be the fluid particles. We'll follow each and every fluid particle and see how the velocity varies as it traverses within the flow domain, and then calculate the required forces for each and every particle within the flow domain. It turned out to be very, very accurate and very, very intuitive. It helps give us very, very detailed idea about the flow system, but turned out to be very, very computationally expensive and difficult to handle numerically and even experimentally. So to tackle that challenge, the macroscopic approach was devised, or the control volume approach was devised, where rather than following each and every particle, we focused our attention to a particular region in the flow domain and see how the flow of the fluid across that particular selected domain imparted force on that particular domain, and how the flow characteristics changed within that domain. So our analysis was again just limited to particular domain, and see how the properties change when the fluid passes through that particular region of interest, which is the control volume in that case. Then we told that for this macroscopic approach to be valid, we need to impose a continuum, a hypothesis that since as you eventually saw, that we are dealing with lots of partial differential equations, and mathematically for these equations to be valid, the derivatives must exist, and for derivatives to exist, these functions, that is treating this velocity field and the pressure field as functions, for these derivatives of this velocity field and pressure field to exist, these functions need to be continuous functions, right? And these functions being continuous was parameterized by a term or a non-dimensional number known as a Knudsen number. Okay, so if Knudsen number was very, very less than 1, it implied that it is a very densely packed systems and continuum hypothesis was valid. But if Knudsen number is much, much greater than 1, we implied that this type of systems cannot be treated as by the continuum hypothesis, and basically this implied very highly rarefied system, that is fluid molecules in the flow domain are much farther apart than the characteristic length scale of the flow. For in the case of, if you are considering a flow through a pipe, and if it is a very highly rarefied system, then fluid molecules in the pipe will be very, very far apart, almost or greater than the diameter of the pipe. Okay, it is distance greater than the diameter of the pipe, and by that you can understand that there is no point of drawing any velocity profile, because no fluid molecules are there to this velocity profile to exist. So our basic, or I won't say basic, our traditional control volume approaches and RTG analysis does not work in the case of highly rarefied systems. Okay, and there was one question in the discussion forum regarding the demarcation between a rarefied system and a, or is there any clear-cut demarcation or a clear-cut value of Knudsen number beyond which we can say that the system will be rarefied? So the answer is that if the Knudsen number is greater than 10, then in that case we consider the system to be considerably rarefied, and we consider it to be a rarefied system. Okay. So then after that we introduced the concept of traction vector. Again, traction vector was introduced to, let me just give me one minute. I'll come back. Yeah. So traction vector was just formally defined to introduce or club in together the contribution of the shear stresses and the pressure forces. Okay, so in the case of fluid at rest, it is free statics. The only forces that exist in the flow domain were the pressure forces and of course the body forces, and but the surface forces that arise in the case of free statics was only because of the pressure forces, and you will see the traction factor eventually boil down to the pressure force. But we know that by now, of course, that when the fluid is in motion, shear stresses will also come into picture. And just to help us to to analyze these shear stresses and the pressure forces together as the surface forces acting on the fluids on the fluid, we devise the traction vector notation, that is force per unit area. But this traction vector was indeed acted as a vector as a dependent on both the direction of the force and the orientation of the area. Okay, and the basic correlation between your shear stresses and the traction vector turned out to be this equation, where Ti denoted the traction vector and tau ij or ji denoted the shear stresses, and nj denoted the normal vector of the area over which the traction vector was evaluated. Okay. Then we also found out that the shear stress tensor is a symmetric tensor, so components such as tau 21 and tau 12 are identical, tau 31 and tau 13 are identical, tau 32, tau 23 are identical. Okay, and again in the assumption that there is no external body couple acting on the system, which is the general case. But of course, if some people are doing specific research studies, then again the picture changes. But for most of the cases and our basic fluid mechanics analysis, and for almost all the cases, this shear stress tensor is identical, similar to the strain rate tensor as well, which is also symmetric. Okay, the both the shear stress tensor and the strain rate tensor are symmetric and thus have 6 independent components. Okay, so just to reiterate, I'm just going through the entire course quickly and like just skimming through it. If there's any specific doubt, you can stop and ask. Otherwise, we'll just go through it as it is planned, because it's just an extra session. So if there's any doubt, you might ask. So one more, I think just a simple relation was the relation between the mechanical pressure and the normal shear stresses. So we found out that there are two types of pressure formally, if you try to define the mechanical pressure and the thermodynamic pressure. And there are some instances when we saw that while discussing the Navier-Stokes equation, that this thermodynamic pressure and the normal pressure are and the mechanical pressure are identical to each other, where the mechanical pressure is defined as this average negative of the average of the normal stresses in the shear stress tensor. Okay, so we have mechanical pressure as minus of tau 11 tau 22 plus tau 11 plus tau 22 plus tau 33 divided by 3, and a negative sign, of course, to show the inward direction of the pressure. So usually, and thermodynamic pressure is obtained by the ideal gas law. So usually these two are identical to each other. In most of the cases, specifically if the Stokes hypothesis is valid, then this mechanical pressure is equal to the thermodynamic pressure. But there are some instances where if the system goes rapid changes and the system does not get enough time to adjust with the rapid changes occurring on the system, then in those kind of scenarios, this pressure, mechanical pressure and thermodynamic pressure are not equal to each other. But for all our given analysis that we have done and the questions that might come in the exam or even any basic fluid mechanics courses, we usually consider the mechanical pressure to be identical to the thermodynamic pressure. Okay, but the definition, since definitions are different and there are instances where these two may not be equal, that's why I just wanted to clarify that. Okay. So this was the basic regime that I wanted to say. I don't know, I discussed it already in the problem-solving session, but the doubt was there. So again, just wanted to point out. So Knudsen is explicitly greater than 10, then we are basically in the rarefied gas system, rarefied flow regime. So after that, yeah, the second week we discussed about the other fluid parameters such as fluid characteristics such as density, then bulk modulus, that is defined as the change in pressure by the volumetric strain. Okay, and then we introduce the concept of Mach number, where Mach number is defined as the flow velocity divided by the velocity of the sound in the medium. So if we are considering air, then the velocity of sound will be different in air than in water. Okay, so we need to consider that separately. So we told that this incompressible assumption is not an explicit assumption or a clear-cut strict demarcation, and it's more like an intuitive understanding that when we say the flow is incompressible, it does not explicitly mean that the density difference is 0, but rather the change in density is less than 5%. So if it is less than 5%, then we consider that the flow is essentially incompressible. Okay. Then we introduce the concept of viscosity. So I think this conceptual clarity I don't think I do need to do, because by now it should be properly understood. But still, I will just see if there's any important conceptual point that I emphasized in the previous lectures, but that might not have been taken in by the students. So I'll just again emphasize it once again, for just as a final revision before the exam. So again, in the week 2 itself we discussed about boundary layers. So I think by now all of you might know properly what boundary layer really means, so I do not think I need to go through it. But other simple implications are that if the viscosity is low, then we have a thinner boundary layer, and the viscosity is high, we have a thicker boundary layer. Again, understood by the fact that the boundary layer thickness scales as 1 by REL to the power half, and REL is U infinity L by nu. So, or basically it will scale as delta by L, scale as nu P infinity by L. So I think now you clearly understand. So if nu is very very large, delta will be large. Higher viscosity will imply thicker boundary layer. Lower viscosity will imply thinner boundary layer. Then there was the Newton's law of viscosity, which basically tells us that the shear stresses vary linearly with the shear strain rate, because in the case of fluid mechanics there is no explicit understanding of shear strain because the fluids tend to deform continuously. So we need to consider the parameter, that is shear strain rate, and this proportionality was equated by using a proportionality constant, which was the dynamic viscosity, or mu. Okay. So in the case of original viscosity, again it's an important conceptual point, that in the case of liquids, this viscosity arises because of the intermolecular forces of attraction between the fluid molecules. But in the case of gases, since these molecules are considerably farther apart compared to fluid, the main cause of viscosity is indeed the transfer of molecular momentum. So since these gas molecules will try to move, will have far more rapid motion in the case of higher temperature. So if temperature increases, viscosity will also increase in the case of gases. But in the case of liquids, since the viscosity is because of the intermolecular force of attraction, and this intermolecular force of attraction reduces when the temperature increases, because as the temperature increases, these molecules will try to move apart from each other. So in that case, in the case of liquids, this viscosity decreases as temperature increases. Okay, again an important point to remember. And the important point to know is that these fluids, all types of fluids do not follow the Newton's law of viscosity, because there are many number of fluids that are non-Newtonian, and the most important fluid that we know is blood, human blood, or any kind of at least human in this case that we know properly, that does not follow the Newton's law of viscosity and in fact is proportional to theta dot to the power 0.7, and that's why it's important to know about, at least know about the different types of fluids which are not Newtonian. So these are dilatant fluid, pseudoplastic fluid, Bingham plastic fluid, and these are the common examples. I don't think in exam they will ask you something like this, but at least knowing that these different kinds of fluid exist is important. So there was an example that I took regarding the apparent viscosity in this week's lecture. So I think if there's any doubt regarding this part, there was an example taken in this week's lecture, so you might want to look into it in the week 2 problem solving session. At least in the problem solving part, in the last part of the video, we had a discussion on a problem on this, so you can take this as a reference. Okay, I will not discuss it for now. So problems part I won't discuss, I won't repeat because we have already discussed it thoroughly. So yeah. So in the third week we discussed about surface tension, basically the force by the virtue of which the fluid molecules on the surface of the fluid are able to retain their shape, and this force per unit length is known as the surface tension or surface tension coefficient. Okay, and in the case of the major relations are the expression for excess pressure and the capillary rise. So in the case of spherical droplets, the excess pressure is given by 2 sigma by r, where sigma is your surface tension coefficient. And in the case of spherical bubble, since bubble will have 2 layers, the inside layer and outer layer, and inside is hollow in the case of spherical bubble, so your excess pressure will basically be 2 times 2 sigma by r, which is 4 sigma by r. Okay, in the case of liquid jet, okay, I think I wrote it, but in the case of liquid jet, your excess pressure will simply be sigma by r. Okay, in the case of capillary rise, basically this fluid will rise in these thin tubes. Okay, again important term is thin tubes, that the fluid will rise in these thin tubes because of the cohesive forces between the liquid molecules and the surface of the tube, which is for example glass in this case. And the major implication of this capillary rise in the nature is the rise of water in the roots of the trees. Of course transpiration plays an important part, but this capillary rise also plays a crucial role in the case of water rise or root shape, as Professor Chakraborty pointed it out in the case of water rise in the roots of the plants. Okay, so the important formula in this case was the capillary rise H was given by 2 sigma cos theta by rho g r, where sigma is the surface tension coefficient, theta is the angle made between the surface of the meniscus. Let me just go here. The surface of the meniscus and the normal of the normal to the this plane surface of the tube or the glass along which the capillary rise occurs. Okay, so basically this angle. So if the cohesive forces are greater than the adhesive forces between the fluid molecules, then this angle will always be an acute angle, that is lesser than 90 degree. But if there are scenarios where the adhesive forces are lesser than the cohesive forces, then I'm sorry, I mixed up. I'm really sorry. Okay, so cohesive forces would mean the force of attraction between the individual fluid molecules within the fluid, and adhesive forces will be the force of attraction between the liquid molecules and the surface at which it is interacting with. So if in general for the many fluids these adhesive forces are much greater than the cohesive forces, and that's why this kind of not much larger, but adhesive forces are greater than the cohesive forces, and that's why this kind of meniscus forms. This convex shaped meniscus is formed. The most common fluid is water, but in the case of scenarios where the adhesive forces are lesser than the cohesive forces, okay, In that case, uh, example of which is mercury in this case. So the formula of the capillary rise changes slightly. So the capillary rise formula is given by 2 sigma cos 180 minus theta by rho gr. Okay, rho is the density of the fluid. In this case, the most common example was taken as mercury. Okay, so the meniscus formed will be a convex shaped meniscus, and you can see the angle formed would be greater than 90 degree, say 170, 180 degree, for example. Okay, so it will, this kind of fluids will form convex shaped meniscus. Then we introduced the concept of hydrostatic law. It is the pressure variation in the case of static fluid is given by given by the balance of the pressure gradient and the body forces. So from this equation you can clearly tell that the pressure will increase along the depth of the fluid, and which was primarily used as the base formula for the measurement of pressure using manometers. Okay, so principle of manometry was also introduced. So sorry, I will not repeat it. It was basically the balance of pressure forces at the datum points. Okay, so given that the fluids at the datum are the same fluid, then only you can equate the pressure, and if the pressure varies, if the fluid varies, then this assumption fails. So then we need to go across the length of the fluid to find the pressure difference. Okay, so again I took a same example in this week. I think this is week 3 if I'm not wrong. This is week 2. So week 3, yeah, week 3. So in week 3 itself we took the example of this. So yeah, this one. So in the week 3 lecture, in the problem solving part, maybe you can go through this example for a proper reference. For in the case of this complicated manometers where there are multiple fluids and it's difficult to have a same uniform datum for all the kinds of fluids, because fluids are changing. Here the fluid is different and all the points, so it's difficult to have a same datum and then measure the forces. So we need to again go to the understanding that pressure increases as you go down and pressure decreases as you go up. With that analogy we have solved this problem. So for your kind reference you might want to look through this for your understanding. Okay, I'm not going to repeat it, sorry. So in the week 4 we discussed about forces on plane surfaces that are submerged in the body. So we found out that in the case of submerged bodies, the pressure forces act through the center of pressure, which is usually at a higher depth compared to the center of gravity of the object, primarily because of the pressure distribution, because pressure distribution increases as we go deeper in the fluid. So the center of pressure at which the pressure forces act is usually lower than the center of gravity of the object. And the center of pressure, the location of center of pressure is usually found out by this relation, that is yp is equal to yc plus ic by ayc, where ic is the moment of inertia of the area moment of inertia of the plane which is dipped in the liquid, and yc is the location of the center of gravity of the object. Okay, so ample amount of examples were discussed in this week 4 week 4 lectures. So I think you might want to revisit it for your practice, and I think that would be good, more than enough. Okay, then we discussed about the hydrostatic forces acting on submerged bodies. So again that can be seen here, and the stability of submerged bodies, and floating bodies. So in the case of submerged bodies, the primary governing factors for the stability of the bodies were the location of the center of gravity and the center of buoyancy. But in the case of floating bodies, the governing factor was the location of the center of gravity and primarily the metacenter. Okay, so if metacenter is positive, then the when the metacentric height is positive, basically it implies that the body is stable, and if it is very small, then the body goes unstable. Okay, so if metacenter is above the center of gravity, the body is stable. If it is below the center of gravity, the body becomes unstable. Okay, so this was a key point to take away, and again, formulas related to it was discussed in the lecture itself. This is basically this formula. So you might want to revisit just for your practice. Okay, these are just formula based type of examples. So the more you solve the examples, the more you get, the more clarification you get regarding the concepts. Okay, so then what there was the concept of rigid body motion. So we just considered the Euler's equation of motion and equated it with the definition of differential of pressure. So we found out how the slope of this free surface of this liquid varies when the cart moves with a certain acceleration. We found out that the slope varies as the acceleration and the exertion by the gravity. So, and unfortunately, I think we didn't have that much in-depth discussion about the rigid body analysis, but the key conceptual takeaway was that even though the fluid in essence is in motion because the cart at which the fluid is being placed is in motion, but since this kind of motion does not result in any kind of motion, relative motion between the layers of the fluid, that's why this kind of fluid motion is also taken under the umbrella of fluid statics. Okay, but unfortunately we didn't take ample example. We only to discuss this part which was covered in the lecture. So, and I do not think that much questions might be asked from the free body rigid body motion, because there were very few examples that were taken, and in the problem solving part also I don't think we took some examples. But for a better understanding, you might want to look at this part of discussion in the problem solving sessions and in the lectures. In the lecture of Prof. Chakraborty, so that would be better. Okay, you might want to visit the lecture. I think I suggest that you might want to visit the lecture and revisit the part where he discusses about the rigid body motion. So examples I won't discuss again. So week 5 we finally started the fluid kinematics. Here we formally introduced 3 flow visualization techniques. That was the streamline, where the equation of streamline was given by this equation, just for your understanding, and streak line, which denoted the locus of the points passing through the same point of injection, and we find the locus of those particles. Okay, and path line, which was the Lagrangian description of the Lagrangian point of view of the fluid motion. So if we consider v to the velocity of the particle and x will be the position of the particle, then if we integrate this equation at different time steps, we can follow the particle throughout the flow domain. Okay, the major conceptual takeaway was that in the case of steady flows, the streamlines, streak lines and path lines are identical to each other. And the other key takeaway was that for most of the flow visualization that we do, say using smoke or dyes, in the case of a wind tunnel, for example, we place a airfoil and pass a smoke through it, and we see some formation of lines, smoke lines over the airfoils. These are actually in essence or by definition streak lines. Okay, but considering that if we're able to achieve or at least able to approximate a steady flow, then since this definition is valid, then these streak lines become identical to the streamlines, and we can say that those kind of smoke lines that we see over the flow over an aircraft wing are essentially the streamlines. Okay, but by the formal definition, they are essentially the streak lines. Okay, so then in this week only we introduced about the convective acceleration part, that is the acceleration because of the spatial variation and the local acceleration, and we found out that from the perspective of control volume analysis, why this type of definition of acceleration was important. So basically we formally introduced the concept of acceleration in the case of control volume. Okay, so then we discussed about 2 types of deformation of the fluid element, is linear and angular deformation. So linear deformation, we saw that basically was the normal components of the strain rate tensor, so elongation along the x, y and z direction respectively, and no cross derivatives. So angular deformation arises when angular deformation will essentially result in cross derivatives such as terms such as dou v by dou y or dou v by dou x or dou w by dou y, dou w by dou x. Okay, or these cross derivatives. Okay, derivatives of the velocity component along the other direction in the flow domain. Okay, so and this angular deformation will essentially arise, or will I must say will only arise if the fluid is in motion. Okay, if the fluid is not in motion, then only linear deformation can occur because of normal stresses. But for the angular deformation to occur, the fluid has to be in motion. Okay. Then we found out or derived the continuity equation that is in vector form in this case, and we solved some examples. So I'll just quickly go through it. Yeah. Then the next week we discussed about in the angular deformation, the stream functions, and velocity potential. So I'll skip the angular deformation part. I do not think it is. So I will just skip this part. Yeah, as I told you, the angular deformation will essentially give rise to your cross derivative components such as dou v by dou x and dou v by dou y. If it is epsilon yz, then y will have the w velocity and z will have the v velocity. So we have dou w by dou y plus dv by dz. So basically angular deformation will give rise to cross velocity derivatives. Okay, and in essence, in tensor notation, the strain rate tensor is defined as this. Okay, we also found out that we can define the angular velocity as such. Okay, so these are just definitions, and I don't think we should dwell much upon the fundamental definitions, so I'll just skip through it. Vorticity we defined as the curl of the velocity field, that is del cross v. The key takeaway from this week was the introduction of stream functions, where the important thing is that the stream functions are only valid for 2D incompressible flows. Okay, so that's why we define psi as function of x and y, and these stream functions essentially converted a equation in terms of u and v to a singular function, that is psi. So we can easily convert this equation dependent on u and v in terms of a single function psi, and if we are then able to solve for psi, we can easily solve for u and v. Okay, essentially finding a way to simplify the problem. And the thing is that this stream function, by its definition, automatically satisfies the mass conservation equation. Okay, so the definition, the simple connection between the streamline and the stream function was that stream functions are constant along the streamlines. Okay, so this was the basic relation between the streamlines and the streamlines and the stream function. And the velocity potential was again used to simplify the flows, and was defined, simplify the flow equation, and was defined for irrotational flows, and is valid for 3D case as well. So the flow only has to be irrotational for the velocity potential to exist. Okay, and we found out that for a 2D incompressible irrotational flow, when all these three conditions are satisfied, this streamlines and the velocity potential lines are perpendicular to each other except at the stagnation points. Okay, so this was the conclusion. And for a irrotational 2D irrotational and incompressible flow, both the stream function and the velocity potential satisfies the Laplace equation, that is del square phi equal to 0 and del square psi equal to 0. Okay, so these examples I will just skip. Then we discussed about the dynamics of inviscid flow, where we introduced the Euler's equation of motion. Okay, this is basically a Navier-Stokes equation without the viscous terms. Then we solved some similar problems to see its implications, and from after this we formally obtained the Bernoulli's equation. So I think we dwelled much more, like we gave an ample amount of time to understand the Bernoulli's equation, where we found out that there were 4 very crucial assumptions while discussing the Bernoulli's equation. So we had the four crucial assumptions were that the flow has to be inviscid, the flow has to be steady, incompressible, or which is density has to be constant, where density is equal to constant is a special case of incompressible flow, and the flow has to be along a streamline. But if the flow is irrotational, then this Bernoulli's equation can be applied to any 2 points in the flow field. Okay, so this is the important list of assumptions that we need to remember, and in exam sometimes they ask questions regarding this. They might tweak one or two assumptions and will say which of the options are correct or which of the options are not required for the validity of the Bernoulli's equation. Okay, so we'll just quickly go through it. Then there was the unsteady for the Bernoulli's equation, and this one which we applied while understanding problems related to the emptying of a tank or time required for the emptying of a tank. So I think in this week sessions, this week examples, you might want to look into it for those examples. So I will just quickly go through it. Like examples such as this, like emptying a tank. Okay, so we have to apply the unsteady Bernoulli's equation and see how the solutions are obtained. Okay, there is a week 7 part. Okay, week 7 examples. We continue with the Bernoulli's equation and take several other examples. So I'll just quickly go through it. And week 8 was again, I think, the application of Bernoulli's equation, and so week 7 and week 8 was had a very condensed discussion on the Bernoulli's equation, basically to end the fluid kinematics part. Okay, where we again introduced flow measuring devices such as venturi meter and orifice meter. So the important point was that again we used the Bernoulli's equation to understand the functioning of this venturi meter and orifice meter, and the important point was that both the venturi meter and the orifice meter were flow measuring devices. So the parameter that they essentially measured was the volume flow rate, but in the sense of measuring flow velocity, we used a device known as the pitot tube. Okay, so and for the final part of the course, we again came to the discussion on the fluid dynamics part, where we started with the derivation of RTT, where RTT was just formally defined as a mathematical transformation for control system to control volume approach. Why? Because all the fundamental equations of physics, there is mass conservation, momentum conservation, were initially devised for control system approach that had a mass of fixed identity. But we know that in the case of control volume approach, even though the mass may be conserved, but the identity of mass is not conserved because there is a continuous flow of fluid across the control volume. So in order to transform the equations from a control system to a control volume approach, we use the mathematical transformation known as the Reynolds transport theorem, which has a canonical form given by this equation, where you just need to change or substitute the value of capital N and small n, where small n is basically the term obtained by dividing the capital N, or small n is the quantity capital N per unit mass. Okay, so we found out that if you replace small n by 1 and capital N by m, we get the mass conservation, and if we replace capital N by mv and small n by v, we get the momentum conservation equation. Okay, then we used similar examples on that. So I think we had detailed discussion, so I think we can skip this part. But how to apply it, I think we need to understand the examples. Okay, so the important part was that here in the case of momentum conservation was that here this VR is the relative velocity between the fluid and the control volume. Okay, and V, I must say here, and the V here is in the absolute velocity of the fluid. Okay, so there are some examples. I do not think we took the example moving vein, but if we consider the example moving veins, that liquid jet stretching or moving veins, in that cases what we can do is we can just simply transform the coordinates, where we can place our reference coordinates to the moving vein, so that the absolute velocity becomes equal to the relative velocity. Okay, so that's how we deal with the problem of moving veins. So such examples are again in the textbook for your reference, so you can just refer them for your understanding. Okay, so here also you can see we discussed about boundary layer, but we didn't have a detailed discussion how this kind of velocity profiles are obtained. But now I think you have a better idea. So in this example, if you remember, we took the concept of streamline where flow does not cross a streamline. That's why we chose this kind of control volume to simplify analysis, and we just did the mass conservation on these 2 points, and we saw that by applying mass conservation we got a relation for h naught, which we eventually applied on the momentum conservation equation to find the expression for the net drag force acting on the flat plate. Okay, so I think this was all from the RTT side. And week 10 we considered the rotating frames. So we discussed the Chesel's theorem, how it is valid for any arbitrary rotating frame, and why we needed to apply this coordinate transformation was because of the fact that the initial Gauni equations were only valid for inertial frames. Okay, but there are some instances or control volumes that are rotating, and any rotating frame inherently becomes non-inertial because of the rotational motion, which includes acceleration. So that's why, to take into account these rotating frames, we had to modify our Gauni equations, and we eventually saw that the final modification was that we basically end up with a velocity, force correction term given by this equation, where A relative is given by, let me go back, by, have I not written it? Yeah, is by these terms. Okay, you will see, you have to see depending on the formula which terms will exist. So if your problem is of just a linearly accelerating reference frame, then all these other terms will get cancelled out, and only the acceleration of the control volume will exist as a correction term. But if the control volume is rotating, then we have to check this other angular velocity terms as well. So we took both examples. I think we discussed very thoroughly the examples of a linearly accelerating object and rotating object, that is the water sprinkler, if I'm not wrong. So you might want to look into this example for the application of this the conservation of linear momentum and the RTT in the case of a accelerating reference frame. Okay, so these are good examples to understand it. Yeah, and in the penultimate week, that is the week 11, if I go back, we formally introduced the Navier-Stokes equation by starting with the momentum conservation equation. So we considered certain assumptions, and that is, first was, if I go back, a stationary reference frame and a non-deformable control volume. Then we found out that the Gauni equation for fluid flow that we get is the Navier's equation or the Cauchy momentum equation, where we see that we have a term known as tau ij. Now if we expand this term, we eventually end up with 9 independent variables, that is 6 shear stress terms, 3 velocity components, and 1 pressure term. Oh no, sorry. We end up with 6 shear stress terms, because the shear stress tensor is symmetric. So we have 6 independent shear stress terms and the 3 independent velocity components. So we end up with 9 variables and 4 equations. The 3 Cauchy momentum equation or Navier's equation along the XYZ direction, and the mass conservation equation. So this inherently makes this equation unsolvable, because we have only 4 equations for 9 variables. So this is not mathematically not possible to solve. It's impossible to solve. So that's why we impose the idea of constitutive relationship, where we represent these shear stresses in terms of the velocity gradients. Okay, and if we do that, then we again end up with variables, that is 3 velocity components and 1 pressure component, that is 4 independent variables and 4 equations, that is the momentum equation along XYZ direction and the mass conservation equation. So if you have 4 variables and 4 equations, basically makes the system consistent, and it is mathematically possible to solve. But we saw that still till now this Navier-Stokes equation is impossible to be solved in the case of a 3D flow, because of the non-linearity existing in the acceleration terms, basically in the inertial terms. Okay, so we again, to simplify our analysis, we found the constitutive relation for Newtonian fluids for just our understanding. In general, this constitutive relation can be for non-Newtonian fluids as well, and several of my professors in my institute work on this non-Newtonian fluids and the constitutive relationship for non-Newtonian fluids. So them, rather than working with the Navier-Stokes, they rather work with the Cauchy-Montaigne equation because of the fact that this is valid for non-Newtonian fluids as well. Okay, but eventually they end up with they find a relationship between the velocity components and the shear stresses, so that they are able to mathematically deal with solving this Navier-Stokes equation or getting a numerical solution as well, but they do not explicitly deal with Newtonian fluids. But for our understanding, we'll deal with Newtonian fluids where our shear stress will vary linearly with the shear strain rate, and after simplifying this tensor equation, we reduce this 4-order tensor to this form, and if you substitute this expression for tau ij in the Navier's equation or the Cauchy-Montaigne equation, we finally ended up with the Navier-Stokes equation given by this equation. Okay, and if we consider the flow to be incompressible, this term will be equal to 0. So this would be the final form of the Navier-Stokes equation that we had to deal with. Then we eventually understood that solving this equation completely was impossible. So we looked into some exact solutions such as flow between two infinitely large parallel plates and flow between pipes. So this was the first exact solution, that is fully developed flow between two parallel plates. So the velocity profile in this case, let me just go back, was found out to vary as this. Okay, where we found out that for the flow to occur in the positive x direction, the term dp star by dx, which is the p star represents the piezometric pressure head, so piezometric pressure, so dp star by dx has to be negative for the flow to occur in the positive x direction. This was the key takeaway, that is basically a negative pressure gradient generated a favorable condition for the flow to occur in the positive x direction. Okay, then there was the concept of average velocity that was found out using these equations, and we found out the relation between the maximum velocity in the flow field and the average velocity, which was u max to be 1.5 times the average velocity. In the case of flow between two parallel plates, the fanning friction factor was found out to be 12 divided by the Reynolds number represented in terms of the channel depth, okay, or half channel depth from this equation. No, it is full channel depth, I guess. Okay, so then we took the example of Hagen-Poiseuille flow or fully developed flow between circular pipe. Again, we solved the equation, Navier-Stokes equation, of course considering several assumptions, and we found out that the final form of the velocity profile was, if I'm not wrong, given by this equation. Vz is minus c by 4 mu r square by small r square, where c was your pressure gradient, that is dp star by dx. Again, for the flow to occur in a positive x direction or positive z direction, in this case, this c, that is dp star by dz, has to be negative, so that eventually both the terms have turned out to be positive. Okay, because this term is positive because small r is always get the radial distance from this axial radial distance from the axial direction or the axis is always lesser than the radius of the pipe if we consider the flow within the domain. So this term is always positive, and if we consider the flow to be positive to be occurring in a positive z direction, so this is positive, so for the entire term to be positive, and we have negative sign here, so c has to be negative for the flow to occur in the positive z direction. Okay, and again we had the similar idea of finding average velocity. So we found out average velocity was given by this equation, and we found out that the relationship between the maximum velocity and the average velocity for the case of pipe flows was that maximum velocity in the case of pipe flow was twice the average velocity in the case of the pipe flow. Okay, and we found out that the fanning friction factor varied as 16 by the Reynolds number depending on the diameter of the pipe, and we found out the Hagen-Poiseuille equation. Then we also introduced the fanning friction factor, the Darcy's friction factor, which varied as 64 times RED, which basically told us that the fanning friction, Darcy's friction factor F is 4 times the fanning friction factor. We also introduced the kinetic energy correction factor in this week. So we took one example where we discussed about the kinetic energy correction factor. and we solved the problem. So the final part was the pipes in series, the uh, what to say, the piping networks. So we had two cases, these pipes in series and pipes in parallel, and we found out that there is a very distinct analogy, clear-cut analogy between piping networks and electrical networks, where we consider the current, electrical current, to be analogous to the volume flow rate and the potential difference to vary as the head loss. We can easily correlate the piping networks and electrical networks. So this analogy part I won't repeat, but it was very nicely discussed in these examples. So we found out that in the case of pipes in series, the head loss in the equivalent piping network is basically the sum of head loss in the two individual pipes, okay, and the flow rate remains constant, okay. But in the case of pipes in parallel, the head loss remains constant in the both the pipes, or all the pipes in the parallel connection, but the volume flow rate across all the pipes is actually the total volume flow rate in the piping network is actually the volume flow rate across the individual pipes, okay. And by using that analogy, we found out some uh, relevant relations, and finally we discussed about the Buckingham pi theorem and why it was important. So we introduce the dimension analysis and then discuss the Buckingham pi theorem. So we found out that for any kind of experimental analysis or experimental setup, if there are m physical parameters in the m physical parameters that govern the entire experimental setup or analysis, and there are n fundamental parameters that define these physical parameters, then the total number of non-dimensional parameters that occur in the experimental setup is m minus n. And the reason to deal with these non-dimensional parameters was that it basically reduced the number of variables that we need to discuss or analyze while formulating the experimental setup. Moreover, dealing with non-dimensional numbers also helped us to make these experimental setups or experimental conditions more uniform across different regions, okay. So if in some regions they cannot, if they are not able to have the exact velocity conditions as something that we are doing here, so rather than prescribing the velocity, we can prescribe the Reynolds number, and they can tweak the parameters such as the viscosity or the length across along which they are measuring the Reynolds number to match our Reynolds number rather than explicitly measuring the velocity conditions. So that's how the Buckingham theorem, pi theorem, turned out to be important, and we then took examples to understand its application. Okay, so I think that's all from my end. I think we very quickly went through all the important topics that we've discussed throughout the course, and if you're watching this video, I don't think it will be very, very helpful because we quickly moved to the concepts, but I pointed out the parts where you might want to look into. So this video you can just use as a revision tool for your before exam. So yeah, so that's all from my end today, and yeah, just to say, I tried really hard to make this semester's or this course beneficial for all the students and all the viewers. So there might have been instances where I was not able to perform my best because of the academic load that I have, and of course my tight schedule. So I tried my best to not postpone or what to say, reschedule any sessions. I think I rescheduled one session, but other than that, I think I conducted all the sessions in the stipulated time. But there might have been scenarios or situations where I was not able to give my best. Like I might not have been at my best, but I tried to rectify it in the next session. So I think I would of course love to hear your feedback, and moreover, if there was any doubt that was pending, I tried to clarify it in the next session. So that also is another point. So I think most of the doubts that were asked by the students was clarified in the problem solving session properly. So that's all. So thank you again for all the participants who actively participated in these live sessions, and all the viewers who watched this video for their clarification. So if there was any thing that I was not able to do properly, or if there's any feedback they wanted to say, please give your feedback. That would be very, very helpful for me, not only for conducting future courses, but also as an academician for further ahead in my life. Okay, so with that, I would just like to say all the best to all of you for your exams, and thank you so much for being a part of this wonderful course. And of course, I would like to thank Professor Chakraborty for conducting this beautiful course, which is very helpful for all the participants and the students, but most helpful for me as a tutor for this course. Okay, thank you and have a very nice day. Okay, and have a very nice exam.